let's consider different cases for the Wald test. So let's say imposing a linear constraint. But before I get into imposing, a single constraint, let me go through the general theory about how to impose a linear constraint or linear constraints. So let's consider only linear constraints of the form Q beta equal to R. So R is constraints, Q is the what we call the transformation matrix to transform beta, to impose the linear constraints. And beta here is the vector of parameters being tested. Q is a matrix of constants that combine the beta, so it transforms beta. So R is a vector of constants. This just means that we can have constraints like, beta 1 minus beta 2 equal to 0. So that's a linear constraints. Beta 1 equal to 0. Beta 1 equal to beta 2 equal to 0. And the Wald statistic, regardless how many constraints we have, has this form for computation. So this is Q beta hat minus R prime, that is transpose of the matrix. Okay. And in the middle, we have this inverse Q, okay, transformation matrix multiplied by the variance covariance matrix of beta, ML, multiplied by Q prime, okay, and then multiplied by Q beta hat minus R. So this is the quadratic formula, right? Quadratic formula. But basically is, as you square that for single coefficient, and then you normalize by this variance covariance matrix of the transformation. So Q beta hat minus R measures the distance in general between the estimated and hypothesized values. And the middle inverse term reflects the variability in the estimator. And why it follows a chi-square distribution, if you know some basics in mathematical statistics, should know that, right? So this is a linear transformation of a ML estimator that follows a normal distribution. So this term should be normal distributed, and this term should be normally distributed. And this outer product, these two, if you square that, and basically for scalar terms, that's like squaring, right? And if you square a normal, then you get what? Chi-square. Then you divide it by the variance covariance matrix. Okay. So for example, here, I'm giving you an example. So we have this model, right? So we have probing model. This is 5 function, right? It's basically integral. And we have y, let's say the response variable, binary response variable, and we have beta 1, beta 0, beta 1, beta 2. 2 covariates and 1 intercept. Let's say for this hypothesis beta 1 equal to 0, what's going to be the Q beta hat minus R looks like? Well, it's going to look like that. So this is Q, this is beta matrix, vector, column vector, and this is R constraints. Because we assume Q beta hat equal to R. So they're equivalent, right? They're equivalent. So Q beta hat minus R is repeated at the end of formula, which squares the distance. And the middle portion is like that, right? So this is Q, this is Q prime. And for a single parameter test, it collapses to 1 over sigma hat square for beta 1 hat, right? The smaller, in general, the smaller the variance, the larger the weight given to the distance, right? That is, the faster in log of L, the log likelihood function is changing around beta 1 hat. More significant, the more significant beta 1 hat minus 0 is. So here's a question for you to think about. Why should we give less weight when the variance is larger? Okay. And combining these results, actually, we can get this. So a Wald statistic, the result should be almost equivalent of z squared, this statistic. And you will see that in our lab guides. How about this hypothesis, right? So beta 1 equal to beta 2 equal to 0. Well, for q beta minus r, it's going to become like that. So we have 2 rows in the matrix Q transformation, right? Then column vector for parameter and R, right? Because we assume, you know, beta 1 equal to beta 2 equal to 0. And if you carry through the computation for the matrix, we get beta 1 minus 0, beta 2 minus 0. Because we assume beta 1 is 0 and beta 2 is 0. Let's say we test 2 coefficients separately as opposed to simultaneously. So this is simultaneously, right? Beta 1 equal to beta 2 equal to 0. How about testing them separately? Will there be any difference? How about testing this one? How about testing next one? So I want you to think about what is the difference? What is the difference between these two? So I mean, there's 3 sets of hypotheses. Are they statistically equivalent hypotheses? If not, then why not? I want you to think about it. You know, it could be in our quiz.